Hi, it's Dr. Lloyd White here again, and in this video we'll have a look at the development of the thorax and the different spaces that we have within the thorax itself. So we'll start off looking at a little bit of embryology, and here we can see a superior view of the trilaminar embryo with a transverse cross-section through it so that we can see the germ layers. We have in blue the ectoderm, which will form the skin and the nervous system. In red we have the mesoderm, which will form our muscles and our bones and our joints, etc. And in yellow we have the endoderm, which will form the lining of our internal cavities and organs. And as this trilaminar embryo folds, the layers all come into contact with each other and squeeze off tubes which become our future viscera, like the lungs and the heart and the digestive tract. So we can see again the ectoderm forming the outer layer of the body wall. In red we can see all the developing muscles and skeleton, and in yellow the developing organs. So we have the somatic mesoderm and the surface ectoderm next to each other, and they will form the body wall. So in our case looking at the thoracic wall. And the splanchnic mesoderm will align the endoderm, which will form the viscera, or in our case the lungs or the heart. And in between the splanchnic mesoderm and the somatic mesoderm will be our coelom, or body cavity. And within this there will be a few different cavities in the thorax, like the pericardial cavity, pleural cavity and peritoneal spaces, cavities in the abdomen and pelvis. Now it's important to note that this body wall will be innervated by somatic nerves, while the splanchnic mesoderm will be innervated by the visceral nervous system, so our sympathetic and our parasympathetic nervous systems. So in this diagram we'll just focus on the formation of the body cavity and the formation of the organ that will fill the cavity. Now if we look at a coronal cross-section through the thorax, the abdomen and the pelvis, we can see the different coelomic cavities that are formed during development. In the thoracic cavity, in the lateral parts, we have two pulmonary cavities, and this is where the lungs will lie. And these pulmonary cavities will contain a further cavity called the pleural cavity. We'll look at this in a future slide. Now, in between the two pulmonary cavities, we have our mediastinum. In the superior part of the mediastinum, we will have our great vessels like the superior vena cava, the aorta, the pulmonary arteries and veins, while in the inferior mediastinum we will have the heart, and the heart will be surrounded by another smaller cavity called the pericardial cavity. Now in the abdominal cavity there will be another smaller cavity called the peritoneal cavity, and this will continue down into the pelvic cavity as well. It's important to realise that these sub-cavities within the major open cavities all develop using the same principles. So if you imagine a full balloon, and the skin of the balloon being the serous membranes. Now these serous membranes start off lining those pulmonary cavities, the inferior mediastinum, the abdominal cavity, the pelvic cavity. But then as the organs start to grow, in this case represented by a fist and a wrist, as they punch into that balloon, those organs are going to end up being surrounded by that serous membrane. You'll still have part of the serous membrane lining the body wall, but you'll also have part of that serous membrane lining the outer surface of the organs as well. And this ends up creating a smaller cavity. So whereas the original size and shape of the balloon represents, say, the pulmonary cavity, now that the organ has grown into that cavity, this smaller cavity between the two layers of serous membrane are those subspaces that I was talking about on the previous slide. So if we're talking about the lungs, this will be the pleural cavity between the body wall and the surface of the organ. So now let's look at this in the same schematic diagram as we were looking at before, just zoomed in a little bit onto the thorax. So laterally we have our pulmonary cavities, and this is the open or actual space. And this will end up containing the lungs and the serous membranes, which to do with the lungs we call the pleural membranes. So the boundaries of the pulmonary cavity are formed by the muscles and the bones of the body wall, the membranes of the mediastinum, and the suprapleural fascia. The parietal pleura will line the internal aspect of the boundaries of the pleural cavity. But then the lungs will grow into this pulmonary cavity, end up being lined by the same serous membrane. So this serous membrane is continuous with the serous membrane lining the body wall. So we'll have the parietal pleura lining the walls of the pulmonary cavity, and the visceral pleura lining the outer surface of the lung itself. And in between the parietal pleura and the visceral pleura, we will have our pleural cavity. And within this pleural cavity, we will have a small amount of serous fluid which will stick these two layers of pleura together so that when one moves, the other moves. And so when the thorax expands, it will pull the lungs out with it, which will increase the volume in the lungs, decrease the pressure in the lungs, and air will rush into the lungs. And this is breathing in, or inspiration. So in a diagram from your prescribed textbook now, we can see the serous membrane with the organ coming in and being lined by visceral serous membrane, or visceral pleura in this case. We have the visceral pleura lining the outside of the lung in the pulmonary cavity, and then we have all the different parts of the parietal pleura lining the internal aspect of the body wall, or the walls of the pulmonary cavity. And in between those layers of pleura, we will have our pleural cavity with a little bit of pleura or serous fluid within it. So the visceral pleura will stick to the parietal pleura via the surface tension produced by the pleural fluid. This will cause a negative pressure so that they'll stick together, and when the parietal pleura moves as we breathe in, the visceral pleura will move with it, and so the lung will inflate. In the event of a collapsed lung, puncture through the parietal pleura will break the surface tension between the pleural layers. Air will enter into this pleural cavity, and the lung will deflate and will no longer be able to breathe using that lung. So let's have a look at these potential spaces again. We have the parietal pleura lining the walls of the pulmonary cavity. We have the lungs within that pulmonary cavity lined with visceral pleura. The parietal pleura will stick to the visceral pleura, and so between the parietal pleura and the visceral pleura lining the lung, we have this potential cavity, this pleural cavity. Now if we look at the inferior part of the mediastinum, we have that being lined by parietal pericardium. Within this inferior mediastinum, we will have the heart, and the heart is lined by visceral pericardium. And this parietal pericardium will stick to the visceral pericardium. We'll have the creation of the potential pericardial cavity. And again, as the parietal pericardium moves, so too will the visceral pericardium. So they'll expand and contract as one. And of course we can see the mediastinum being all of this space between the pulmonary cavities. So the heart and the pericardial cavity is located within the mediastinum. So for further reading, you can consult your prescribed textbook. The study guide will have the list of learning objectives that your assessments will be based off of, and the principles booklet can help you if you're stuck with understanding the principles governing the formation of open spaces and potential spaces. And again, if you have questions about this content, you can ask them on the LMS discussion forum, and I will tend to them and help answer those questions for you. And hopefully you'll get a better understanding of what we're talking about. So this is Dr. Lloyd White. Thanks again. Bye.